Good morning, everybody. My name is Rufal Mercuria. I'm just gonna give a quick overview of our work that we did together with Unified Streaming and Varnish Software, with Roberto, Espen, and Arjen. So for details, I refer to the paper. I'm just gonna give a quick overview. So the topic of today is targeted media presentations. So this is basically the idea is that we want to see what we like. We want to view what we like and or what suits us. So for that we use existing or live content. So the idea is to make it more personalized or targeted. In the examples that we do, we more focus on pre-roll and mid-rolls. But you know, the next step could be including things like fast channels. So this is like an opportunity to make the streaming more targeted to the users. So the point of the state of the art is that either we are very strong, we basically transcode everything, or we are smart and maybe a beautiful solution that's implemented in the player, such as a multi-period dash or VAST or SMIL. These standards allow for customized playback, but they introduce backward compatibility at players. So we're going to present an approach that combines the best of both worlds, which is offline transcoding and just-in-time packaging. So when we were looking at the problem, we know there are standards for the players to combine different contents. But when you really look at the implementation on different devices, and if you want to support all streaming protocols or formats, then we found that the common denominator is basically what is in MP4, is like a single media timeline. So our solution is basically to repackage different content, either live or stored, to a continuous timeline on the fly. And then we have offline transcoding before that. So I'm going to detail, all of this solution. So here is sort of an overview. So there are two parts that we describe in the paper. We have the content authoring part, which is two parts, an offline transcoding. So we transcode to fragmented MP4 or CMAF, basically single tracks per file. In the next slide, I will provide some more details on the transcoding part. Then we use a just-in-time packager to package on the fly, on request, the presentation to a continuous timeline, which means that it can be played as an MP4, a dash, an HLS, or a smooth, and that it will be played on most devices, even more legacy devices. In doing so, later in this presentation, I will present that now instead of having problems at the receiving players, we actually get some problems in the CDN. So that's where most of the research and technical work in this paper is done. So I'll come to that later in the presentation. So this we call the media delivery component. So basically we present the framework with two components, the content authoring, which is transcoding to CMAF, FMP4, and just-in-time packaging, and then the delivery component, which includes a smart edge cache to enable efficient caching of the targeted media presentations. So that's also where the collaboration with Varnish came in. So with regards to the transcoding is we transcode to the common media application format or fragmented MP4, which means a single track per file. In addition, we added some additional constraints. So we aligned the bit rates of different contents. It will become clear why we do that later. We use the same segment duration for the contents. We align the segment boundaries so the main point is to create interchangeable segments. And also the audio and time text is transcoded in this kind of format. And some of the formats that we mostly based on, or this image is based on, is on the CTA 5001 content specification. So it's basically aligning well with the standards work that is going on in the CTA. So with regards to the authoring, it's basically two steps. So first, the content is offline transcoded to single tracks for each representation or rendition. Then we use a just-in-time packager, which is based on our solution from Unified Streaming using Unified Origin. And we can use a SMILE playlist to make a customized playlist. So SMILE is an old W3C standard that can be used to create customized presentation where you can basically have sequencing or parallel of sequential or parallel playback of different contents, and that's used by the packager to create a metadata file, and that way we can play out the playlist as a single continuous track. Okay, and that can go in different protocols, including HTTP live streaming, Dash, and so on. So that's the content authoring part. And then, yeah, the problems start with the media delivery. So as most of you will know, that HTTP-based delivery is very much depending on the content delivery networks and the cache keys provided by the object identifiers, so basically the URI or the URL. But with this repurposing of content for different users, we create a separate presentation for each targeted stream or possibly for each user. So we have a difficulty to cache and deliver the content. So this is why we introduced this Smart Edge component using Varnish, and we implement two ways to enable the caching of these personalized playlists. So the first approach uses a hash-based approach using the Fowler-Null-Vo hash. So basically what happens is when a GET request comes to the Edge proxy cache, the proxy cache will it will compare in its lookup table to see if it computes the hash, and it will look in the lookup table if it's already sorry, I'm going too fast here. So the first step is to do the head request to the origin or to the JIT packager to basically receive the corresponding hash, which is returned in the head request, and that way we can compare with the stored items in the content table if it's already stored. So if it's already stored, then we can just return the media segment because we look it up based on the hash. Otherwise, another request will go to the JIT packager to get the segment, and then the segment is returned. So this is the hashing-based approach. So instead of having more GET requests, we introduce a head request, which has lower overhead. Then in the second approach, we develop a naming scheme. So in this case, we basically use the segment naming, and the main constraint here comes from Dash, which uses basically segment template and segment timeline. So there you cannot just choose any name, so we developed a naming scheme in which we encode some of the object properties. So that way in the Edge proxy cache, we can basically identify based on the strings in the URL by a regular expression in Varnish, like what the content is, and based on that we can look up the content, and either if it's cached already we can return it, and otherwise we have to do another request to the origin server to get the object, and then we store it. So there are two approaches for the caching. So with regards to the naming, we basically encode asset IDs in the segment name. So it starts with asset ID, and then we use separator, and then the start on the continuous timeline, and then the duration of the asset. So it can be an ad or a main content, and then we include the separator and the content type, codec type, and so on. But it also includes the bit rate. So that's why we align the bit rates of each of the contents so that they can be interchangeable, so that this swapping can be done. So we can basically swap segments at the Edge cache based on the asset ID, and also store it based on that. So this was implemented in the Varnish commercial version using VCL. So VCL is the Varnish configuration language that makes it like easier to write programs that can be implemented in Varnish that can run very fast. So that was implemented, and in that scheme we use the asset ID and the timing to store the different content components in the cache. So to confirm the approach, we did some test cases, some test playlists with different pre-rolls and mid-rolls. We considered two cases, one where the cache is not loaded and one where the cache was loaded with playlist A. So in this experiment, we basically have 5 playlists with different mid and pre-rolls. In this case, we are testing that basically playlist A is loaded, and then we test the other playlist after that to see if the caching is functioning properly. So a first test is just on the response time. So here there are 2 cases, one where the cache is not loaded, so there's no playlist that's been played. So in this case, you will see that the hashing approach has the largest response time overhead, but it's relatively small. And the CDN and the naming scheme. So the CDN is basically a traditional CDN with a normal cache key based on the segment object name. Has the lowest response time. But then after playlist A, if playlist A is loaded in the cache, then you can already see the benefits of the approach. So here we see that that the naming scheme, because the naming scheme can detect deduplicate basically objects, will have a lower response time, while the hashing-based approach and the CDN-based approach will have a larger response time. This is the case where the cache was already loaded with one previous playlist, so that a lot of the duplicated content is already cached using the hashing approach or the naming scheme approach. So here you can see that, for example, in terms of the cache size, which when the cache size increase for playing an additional playlist is much higher for the traditional CDN-based approach, and for the naming and hashing scheme approach, it's much reduced, which was actually the objective of this prototype. And the same for the backend traffic, which is often something that implementers want to save on because it implies costs, basically. Egress cost from your origin is also heavily reduced. So that was the prototype. So I'm just going to give a quick summary of what we showed. So we basically tried to do a repurposing of content to stream to a broad range of devices by making a continuous timeline. It has an authoring component with offline CMAF transcoding with both segment and bitrate alignment so that we can create interchangeable segments. And then we have the authoring part, the subcomponent with the just-in-time packaging, which creates on the fly the manifest or the streaming playlist with the repurposed presentations. And then to enable the HTTP delivery, we did the optimized caching using the naming scheme and the hashing scheme. And the POC was implemented using Varnish Enterprise, and the origin was based on Unified Origin, where we evaluated it. We showed that it has low response time, reduced backend traffic, and reduced cache sizes. And the next step, we are looking to deploy this at larger scale in real deployments. So I think there is a time for questions. And also, if you want to reach out, there is my contact details and my colleague Roberto, who has done a lot of this work. So thank you for your time.
We have time just for one question, if somebody wants to ask something. Anybody? Okay, please go.
Thanks, Rafael. Very good talk. So I have a question on the, if you had any experience with the thundering herd problem. Like, if many clients hit you asking for the same segment and you're transcoding it. I don't know, maybe Varnish has some tools to do that, but that's a long delay, right, for the transcode?
Yes. Yeah, so we looked at that. We found that in Apache we couldn't get protection against thundering herd. In Nginx, I think we found a solution for that, and also in Varnish. So this is also one reason why we are looking at the Varnish implementation. Thank you.
Thank you very much. Let's thank the speaker.